In this lesson, we'll introduce the Laplace transform, a tool that converts time domain functions into the S-domain to make differential equations easier to solve. The Laplace transform of a function f of t is written L of f of t equals f of s, and is defined as the integral from 0 to infinity of e to the negative st times f of t dt. Intuitively, the kernel e to the negative st weights the function in time. Let's visualize with a simple time domain function, f of t equals 1, and the kernel e to the negative st. We will see how changing s changes the weighting. Here s is usually a complex number, s equals sigma plus I omega, but for understanding the weighting behavior, we can think of s as a positive real number. Larger s means faster decay, and thus less contribution from later times. Let's compute a simple example. For f of t equals 1, the Laplace transform is the integral from 0 to infinity of e to the negative st dt. We'll evaluate that integral step by step. That transform is solving ordinary differential equations. Here is a short worked example. Y prime equals y with initial condition y of 0 equals 1. Take the Laplace transform of both sides. The transform of y prime is sy of s minus y of 0, and the transform of y is y of s. We then get an algebraic equation in y of s. Substitute the initial condition y of 0 equals 1. Rearrange and solve for y of s. We find y of s equals 1 over s minus 1. Taking the inverse Laplace transform gives y of t equals e to the t. To summarize, the Laplace transform converts time domain functions into the S-domain, where differential operators become algebraic multipliers. After solving algebraically, we use the inverse Laplace transform to return to the time domain. If you'd like, we can explore more examples or tables of common Laplace transforms. Thanks for watching. If you want, I can make another video on inverse Laplace transforms or build a table of transforms to use as a quick reference.